In the late 1930s, engineers set out to build what many believed would become one of the most beautiful suspension bridges in the world. Stretching across the Tacoma Narrows Strait in Washington state, the bridge was designed to connect communities and dramatically reduce travel times. At the time, it represented the future of modern engineering: elegant, lightweight, and remarkably efficient. Compared to earlier suspension bridges, the Tacoma Narrows Bridge used a slimmer design that required less steel and significantly reduced construction costs. To many people, it was a masterpiece. Construction moved quickly, and excitement grew as the project neared completion. When the bridge finally opened to traffic on the 1st of July 1940, thousands of people came to witness the event. Newspapers praised its beauty, drivers admired its sweeping views, and engineers celebrated what appeared to be another major achievement in bridge design. But hidden beneath that elegant appearance was a problem nobody fully understood. Almost immediately after opening, something unusual began to happen. When strong winds passed through the narrow strait below, the bridge started to move. Not a little, a lot. The roadway would rise and fall in large rolling waves. Drivers reported feeling seasick while crossing. Passengers described the experience as riding on an ocean swell. Some people were fascinated. Others were terrified. The bridge quickly earned a strange nickname: Galloping Gertie. At first, the movement seemed more amusing than dangerous. After all, the bridge remained standing. Traffic continued to cross, and engineers believed the issue could eventually be solved. But what looked like a harmless curiosity would soon become one of the most famous engineering failures in history. Many engineers remained confident. They believed the bridge's movement was simply an inconvenience rather than a serious structural threat. Small adjustments were discussed. Possible solutions were considered. And few people imagined that the bridge's unusual behavior would soon attract worldwide attention. Because just 4 months after opening, the bridge would destroy itself. As traffic continued to cross the Tacoma Narrows Bridge, its unusual behavior became impossible to ignore. Almost every day, the bridge moved. When winds swept through the narrow channel below, the roadway would begin rising and falling in long, rolling waves. Drivers could actually see the bridge bending beneath them. Some vehicles bounced up and down as they crossed. Others slowed to a crawl, unsure of what they were experiencing. The motion was so unusual that many local residents came simply to watch. Photographers captured images of the bridge flexing in the wind. News reporters began covering the phenomenon, and before long, the bridge had become something of a local attraction. Its famous nickname, Galloping Gertie, spread throughout the region. People joked about the bridge. Visitors stopped to observe it. Some even crossed it just to experience the strange motion for themselves. But behind the curiosity and amusement, engineers were becoming increasingly concerned. Large bridges are designed to move. Expansion, contraction, and minor vibrations are completely normal. But the Tacoma Narrows Bridge was behaving differently. The movement was becoming larger than expected. And more importantly, it was happening repeatedly. On windy days, the bridge seemed almost alive. The deck would rise, then fall, then twist slightly before returning to its original position. Witnesses described the motion as similar to waves rolling across the surface of the ocean. Several attempts were made to reduce the oscillations. Engineers installed hydraulic dampers designed to absorb some of the movement. Other modifications were proposed and tested, but none of the solutions proved completely effective. The bridge continued to sway. It continued to bounce, and each windy day seemed to produce the same unsettling results. Some drivers refused to cross it altogether. Others reported feeling nervous every time they approached the structure. Even experienced engineers struggled to explain exactly why the bridge was moving so dramatically. At the time, the science of aerodynamic behavior in long-span bridges was still developing. Many of the tools and testing methods used today simply did not exist. As a result, the true danger remained hidden. What appeared to be a strange but manageable problem was actually a warning sign. The bridge was revealing a weakness that nobody fully understood. And with every passing week, the risk continued to grow. Yet despite all the attention, the bridge remained open. Cars continued to cross. People continued to watch. And few realized that the countdown to disaster had already begun. For months, engineers searched for answers. Why was the bridge moving so dramatically? At first, many experts believed the problem was relatively simple. Strong winds were passing through the Tacoma Narrows. The bridge was lightweight, and the structure appeared to be unusually flexible. The assumption seemed reasonable, but the real explanation was far more complex. To understand what happened, we need to understand how suspension bridges behave. Unlike solid concrete structures, suspension bridges are designed to move. They expand and contract with temperature changes. They respond to traffic loads, and they flex under wind forces. A certain amount of movement is completely normal. The problem begins when movement starts feeding itself. And that is exactly what was happening on the Tacoma Narrows Bridge. As winds moved across the structure, they created forces that pushed and pulled on the bridge deck. Normally, these forces are small enough for a bridge to absorb safely, but the Tacoma Narrows Bridge had an unusually narrow and flexible design. Its roadway deck was slimmer than many engineers now considered safe. This made the structure vulnerable to aerodynamic effects that were not fully understood at the time. As wind flowed around the bridge, it began generating oscillations. Small movements became larger movements. Larger movements created even stronger aerodynamic forces. Those forces generated even more movement. The cycle continued repeating itself. The bridge was no longer simply responding to the wind. The bridge was interacting with the wind. And that distinction changed everything. What made the situation particularly dangerous was that the bridge appeared stable much of the time. On calm days, traffic crossed normally. Drivers saw no obvious signs of imminent failure. The structure looked strong. The towers stood firm. The cables remained intact. From a distance, everything seemed perfectly safe. But engineers were beginning to realize that the problem wasn't located in the towers or cables. The problem was hidden within the behavior of the bridge deck itself. The roadway had been designed to be thin and lightweight. This reduced construction costs and improved efficiency. However, it also reduced the structure's ability to resist certain aerodynamic forces. As wind flowed around the deck, air pressure changed continuously. Instead of passing harmlessly around the bridge, the airflow began interacting with the structure in unexpected ways. Each movement altered the airflow, and the altered airflow created even more movement. The bridge had effectively entered a feedback loop. This is one of the reasons the Tacoma Narrows disaster became so important in engineering history. It demonstrated that wind is not simply a force acting on a structure. In some situations, the structure itself can influence the wind around it. When those interactions become synchronized, movement can grow rapidly and unpredictably. Videos recorded before the collapse show the bridge twisting dramatically from side to side. Sections of the roadway appeared to move independently. At times, the motion looked almost impossible. Many observers could hardly believe that a bridge could behave that way without immediately collapsing. Yet the structure continued standing, and that created a false sense of security. Each day the bridge survived seemed to suggest that the problem was manageable. But the forces building inside the structure were becoming increasingly severe. Engineers observed the motion. Measurements were taken. Reports were written. But despite growing concern, nobody fully understood the scale of the danger. At the time, wind tunnel testing for long-span bridges was still in its early stages. Many modern engineering tools had not yet been developed. Computer simulations did not exist. Advanced aerodynamic modeling did not exist, and engineers were entering territory that few had explored before. As the months passed, the bridge continued behaving in increasingly unusual ways. The roadway twisted, the cables vibrated. Sections of the structure moved in ways designers had never expected. What looked like a strange curiosity was actually a warning. The bridge was revealing a fundamental flaw in its design, but the warning was not fully recognized. And by the time engineers began to understand the problem, there was very little time left. The phenomenon responsible for the disaster is now known as aeroelastic flutter. Unlike ordinary vibration, flutter can continuously increase in strength when conditions are right. Instead of dissipating energy, the structure begins feeding energy back into itself. The result is a self-amplifying cycle. Each movement becomes larger than the last. Each oscillation becomes more violent, and eventually, the structure can no longer withstand the forces acting upon it. The warning signs were visible. The movement was visible. The danger was visible. What remained invisible was how close the bridge was to failure. Today, aeroelastic flutter is studied by engineering students around the world. It has become one of the most famous lessons in structural engineering history. But in 1940, it was still largely misunderstood. And the Tacoma Narrows Bridge was about to become the experiment that taught the world a very expensive lesson. Because on the morning of the 7th of November 1940, everything finally went wrong. On the morning of the 7th of November, 1940, conditions at the Tacoma Narrows Bridge were far from unusual. Strong winds were blowing through the narrow strait, but for Galloping Gertie, movement had already become a familiar sight. The bridge had been oscillating for months. Drivers, engineers, and local residents had all witnessed its strange behavior before. At first, the motion seemed similar to what had been observed many times earlier. The roadway rose and fell, the structure twisted, and the bridge continued flexing under the force of the wind. But this time was different. As the morning progressed, the oscillations became increasingly severe. Witnesses watched in disbelief as sections of the roadway began moving dramatically up and down. The bridge no longer appeared flexible. It appeared unstable. Traffic was stopped. Officials quickly realized the situation was becoming dangerous. Most drivers managed to leave the structure safely, but the bridge itself remained trapped in a battle against forces its designers had never anticipated. The twisting motion continued growing stronger. Steel components groaned under enormous stress. Suspension cables shook violently. The roadway bent in ways that seemed impossible for a bridge of its size. Photographers and engineers captured footage of the event. Those images would later become some of the most famous recordings in engineering history. By this point, the bridge was experiencing motions far beyond anything seen during normal operation. Witnesses described the roadway as twisting like a ribbon in the wind. Some sections appeared to rise, while others dropped dramatically. The movement was no longer merely uncomfortable for drivers. It had become a clear sign that the structure was losing its ability to resist the forces acting upon it. Engineers watching the event realized they were observing something extraordinary. The bridge was demonstrating a failure mechanism that had never been fully understood before. Every minute, the oscillations grew more violent, and every minute the chances of saving the structure became smaller. Then the structure reached its limit. A section of the roadway suddenly failed. Concrete and steel crashed into the water below. Moments later, additional sections followed. Piece by piece, the bridge began tearing itself apart. The collapse unfolded before the eyes of shocked witnesses. Within a matter of hours, one of the most celebrated bridges in America had been reduced to wreckage. Remarkably, no human lives were lost during the disaster, but the engineering consequences were enormous. The collapse immediately attracted worldwide attention. Engineers across the globe studied the footage. Universities analyzed the failure, and the Tacoma Narrows Bridge became one of the most important case studies ever recorded. The bridge had stood for only 4 months. Yet its failure would influence bridge design for generations to come. In the aftermath of the collapse, engineers faced an important question. What exactly caused the Tacoma Narrows Bridge to fail? At first, many people blamed the wind itself. After all, strong winds were present on the day of the disaster. But further investigations revealed that the real problem was far more complicated. The bridge did not collapse simply because the wind was strong. It collapsed because of the way the structure interacted with the wind. The Tacoma Narrows Bridge had been designed with a very narrow and flexible deck. This made the bridge lighter and less expensive to build. However, it also made the structure vulnerable to aerodynamic instability. As wind passed around the bridge, it generated forces that caused the roadway to move. Those movements altered the airflow. The altered airflow created even greater movement. The cycle repeated over and over again. Instead of reducing vibration, the bridge began amplifying it. Engineers now refer to this phenomenon as aeroelastic flutter. Unlike ordinary vibration, flutter can continuously increase in strength once certain conditions are reached. The structure essentially feeds energy back into itself. Each movement becomes larger than the last. Each twist becomes more severe. And eventually, the forces exceed what the structure can withstand. The collapse changed engineering forever. Researchers began studying how wind interacts with bridges in much greater detail. Before Tacoma Narrows, many bridge designers focused primarily on structural strength. If a bridge could support its own weight, traffic loads, and expected environmental forces, it was generally considered safe. The collapse revealed that strength alone was not enough. Engineers also needed to understand how a structure would behave dynamically over time. A bridge could be strong and still fail if its interaction with wind was not properly understood. This realization changed the way engineers approached large-span structures. For the first time, aerodynamic behavior became a critical part of the design process. Researchers began conducting extensive experiments to understand how wind could influence bridges, buildings, towers, and other flexible structures. Wind tunnel testing became standard practice for major bridge projects. Engineers developed new methods to predict aerodynamic behavior long before construction begins. Modern suspension bridges are now designed with lessons learned directly from Tacoma Narrows. In many ways, the bridge failed, so future bridges would not. Its collapse was expensive, it was embarrassing, and it shocked the engineering world. But it also transformed the science of bridge design and helped make future structures safer than ever before. The Tacoma Narrows Bridge stood for only 4 months. Just 4 months. After years of planning, design, and construction, one of America's most ambitious bridges disappeared in a matter of hours. For most projects, that would have been the end of the story. But for Tacoma Narrows, it was only the beginning. The collapse shocked the engineering community. Newspapers around the world reported the disaster. Photographs spread rapidly. And perhaps most importantly, the entire event had been captured on film. For the first time in history, engineers could repeatedly watch a major structural failure unfold. They could study it frame by frame, analyze every movement, and learn directly from the disaster itself. The bridge became a classroom for an entire generation of engineers. Universities began using the footage in engineering courses. Researchers spent years investigating exactly what happened, and the lessons learned from Tacoma Narrows would influence countless future projects. Before the collapse, many designers focused primarily on strength. Could the bridge support traffic? Could it withstand its own weight? Could it survive expected environmental loads? Tacoma Narrows revealed a different challenge. A structure could be strong and still fail. Understanding how wind interacts with a structure became just as important as understanding concrete, steel, and cables. The disaster accelerated research into aerodynamics. Wind tunnel testing became increasingly important. Engineers developed new methods to analyze vibration, resonance, and structural behavior. Many of the safety standards used today can trace part of their history back to the lessons learned from Galloping Gertie. Modern suspension bridges look different because of Tacoma Narrows. Modern bridge testing exists because of Tacoma Narrows. And modern engineers continue studying the disaster more than 80 years later. In a strange way, the bridge became more famous after its collapse than it ever was while standing. Today, a replacement bridge crosses the Tacoma Narrows. Thousands of vehicles use it every day. Most travelers never think about the structure that came before, but engineers do, because hidden behind every successful design is a history of failures, mistakes, and lessons learned. The story of Galloping Gertie reminds us that engineering is a constant process of learning. Every project teaches something, every mistake reveals something, and sometimes a single failure can change an entire profession. The Tacoma Narrows Bridge survived for only 4 months, but its lessons may last forever. Thank you for watching. If you enjoy engineering failures, mega projects, and real-world construction stories, be sure to subscribe for more videos from Ant Hill's BuildVerse. Because some of the world's greatest